Today we're going to start section 9.1 and we're going to take a look at sequences. Chapter 9 is my favorite chapter in everything we're going to be covering this semester. It may or may not be your favorite chapter. I do feel like that it has this sort of feel that I think it's chapter 8 in your Calc 2 book did, where it was integration techniques and you had to sort of examine what that was to try and figure out what technique to use to find the integral. It feels a lot like that with some of the things we're going to do throughout this chapter where you're analyzing things to try to figure out what method do I use. So kind of like a puzzle. So we're going to start with a definition. And it's the definition of actually what a sequence is. So a sequence is a function whose domain is the natural numbers. Is that too small? Can you guys read okay? Okay. Do you remember what natural numbers are? You got lots of numbers.
1, 2, 3, 4.
Yeah. So we call them natural numbers because they're the ones you naturally start to count with. Sometimes you hear them called the counting numbers as well. So 1, 2, 3, 4, and so on. Yeah. Though subscript notation is commonly used. So instead of thinking about 1 and 2, we often use subscripts. So we say something like A1, A2 when we're working with these. The values A1, A2, and so on are the terms of the sequence. A sub n is the nth term of the sequence. Okay, so what we're going to actually do first is we're going to take a look at a sequence as an example. So our example, first example, we're going to write the first 5 terms of the sequence. And while sometimes we're given the sequence and we're looking for patterns and so forth, what we're being asked on this one actually is a case where it gives us like an equation, right, for what our sequence will model. And so here we have 4 over n factorial. And I did choose this on purpose because I want to make sure that you remember factorials because they are going to come up from time to time throughout this chapter especially. Do you remember, let's just do an example of one actually first. So I'll just write it to the side. Do you remember what it means when you have a factorial, like a 5 factorial? Yeah. So it means we take the number 5 and we multiply it by the numbers decreasing by 1, or all the natural numbers down to 1. And that's 5 factorial. Okay, so given that as a reminder, we're going to take a look at the first 5 terms. So we're going to find A1. So A1 would be 4 over 1 factorial. 1 factorial is not very exciting. It's just 1. So the first term is 4. A2 would be 4 over 2 factorial. Well, 2 factorial is only slightly less not interesting than 1 factorial. It's just 2. So when I multiply and divide and so forth, on this one I get 2. A3 means I have 3 factorial on bottom. So 3 times 2 times 1 is what? 6. So I have 4 over 6, but then I would reduce that to what? 2/3. We have a couple more. We're supposed to go to 5 terms. A sub 4. So this is 4 factorial over 4. I'm sorry, 4 over 4 factorial. So I have 4 over 4 times 3 times 2 times 1. And while it's perfectly fine if you want to multiply the 4 times 3 times 2 times 1 out, if you're paying attention so that you catch when these things happen, you can also just reduce things as you go. So this 4 and this 4 will cancel, leaving me with just 1 on top and 6 on bottom. And we lastly have a sub 5. So we have 4 over 5 factorial. So this is 4 over, and I have 5 times 4 times 3 times 2 times 1. And once again, my 4s will cancel on the top and the bottom. So I'm left with 1 on top. And what does the bottom equal on that one? 30, yeah. So what we would answer, I mean, this is the work. And do you have to show every little bit of this? Absolutely not. But you should not just write down A1 equals 4 and A2 equals 2. There's something that goes on in between there. Show me something that you know where the pieces are falling into place, okay? Yeah, don't do that. The reason I say that too is because your calculator will do that. You could stuff this in your calculator and tell it, like you could give it this equation and it could give you those sequence of values quite quickly. So I want to make sure that you understand how it works for the moment, okay? But the answer then to the question is the sequence. So it's 4, 2, 2/3, 1/6, and 1/30. Those are the first 5 terms that we were asked to find. Any questions on that? Okay, so we're going to take a look at another definition. This one's a bit longer, but it will feel familiar to things you've done in other calculus courses. We're going to let L, hang on, I use a capital L, I will too. Let L be a real number. Any idea what L might represent?
Limit.
It's a limit. That's exactly right. So the limit of the sequence and they put them in curly braces when they're representing the whole sequence. You see it written as A sub n when it's representing simply a term of the sequence. So this is the sequence notation, okay, A sub n is L written, again, more familiar notation from calculus 1 actually, limit as n goes to infinity of A sub n equals L. If, you know what that symbol means? You guys seen that one before? It's for every or for all, so we'll just change it till the context of our sentence, right? This would be for every epsilon greater than 0, there exists, that's that E that goes backwards, there exists a capital M greater than 0, such that A sub n minus L is less than epsilon whenever n is greater than that capital M. If the limit of a sequence exists, so limit L of a sequence exists, the sequence converges. To L. If the limit of a sequence does not exist, then the sequence diverges. And converging tends to happen in sort of like asymptotic ways, right? Things leveling off at certain values, if you think from a function or a graphical perspective. Sequences diverging can happen in a couple of ways. One way that they can happen is if the limit of something goes to infinity, right? So like just imagine like having a sequence of the natural numbers, 1, 2, 3, 4, 5, it diverges, right? Because it increases forever. It doesn't ever have an upper bound, like a capping, ability. Another way a sequence can diverge is if you think about things like trig functions where things oscillate, right? Sine values, right? They just keep going, they just keep bouncing back and forth between values, but they never get really close to anything, right? So that would be another example of a sequence diverging, but in a different way. We have some limit properties, and it's kind of like the limit properties from Calc 1. Everything that you would hope to be true is, right? So that's what you're going to look at. You're going to be like, well, yeah, that seems reasonable, and it is. So these are the limit properties. So we're going to let the limit of a sub n as n goes to infinity be equal to L. So it has a limit, that's what we're saying. And we're going to do another one, and we're going to let the limit as n goes to infinity of b sub n be equal to k. And what we're wanting to do is we're wanting to combine these sequences in the basic ways of order of operations. So if you think about that, back when we did these with functions in Calc 1, you want to do things like add them together, subtract them, multiply them, divide them. And those are the basic operations that we're looking at. So the limit as n goes to infinity, and if we add or subtract, we can actually group those two properties together, a sub n plus or minus b sub n. So if that's the case, then we get L plus or minus k. No big surprise, right? Each piece has its own limit, so when we add or subtract them, they go to that sum or that difference of those limits. The second one talks about actually a scalar multiple. So if we have the limit as n goes to infinity of c times a sub n, I don't know why I wrote that so big, then the c, that is the constant, simply gets multiplied by the L. And it almost feels like this c is sort of coming in front of the limit, right? That's what you're having, so you just have c times L. The third one is multiplying them together. So the limit as n goes to infinity of a sub n times b sub n. And what would we expect it to be? LK, right? They're just multiplied, L times K. The last one is division, and it is also the same with one caveat because we have a denominator we have to be careful of. It's a sub n over b sub n. And so this will equal L over K as long as b sub n is not 0 and K is not 0. because it can't divide that, and I've got two denominators I'm dealing with. Any questions so far? All right, we'll stop there for today.